All right. Good morning. As people are trickling in, we get started here and welcome you to the distinguished lecture sponsored by the Information Science and Technology Center, also called ISTEC, here at CSU. Just a couple of words about ISTEC for those of you who are unfamiliar with us. The Information Science and Technology Center here at CSU deals with all aspects of the information sciences and technologies that are going on at CSU, including aspects of research, education, and as well as outreach. One of the events that we host every semester is this distinguished lecture series, of which we have many lecturers who visit us who are distinguished members of their research communities. Today we are very privileged to have a very distinguished lecturer, but to introduce our speaker for today, I'll ask Indrakshi Ray to come up from the Computer Science Department.
So it's my great pleasure to introduce Dr. Shomesh Jha. He is the Lubar Endowed Chair Professor in Computer Science at University of Wisconsin-Madison. He's a student of Edmund Clark, who got the Turing Award 6 years back. And Shomesh has been very influential in a number of security community for sure. He does work in security, formal methods, and machine learning. So I've known Shomesh for a while. He has, he's made. He has done, very pioneering work. There is a lot of work on attack trees, attack formalization. Shomesh was behind it. The earliest to, start work on adversarial machine learning. So he has, won a number of awards. He's extremely modest and shy in that sense. He doesn't list his awards. He doesn't, he's very humble and modest actually. And that's another reason, and very approachable. So, and extremely helpful. And for those of you who remember Lorenzo Di Carli, whom we hired but lost, Lorenzo happens to be, his student. So without...
He has very fond memories.
And without, taking too much of the time, I'll let him get into his talk, and I'm sure all of you will have lots of questions. Yes.
Just to be, it is a real honor to be here, and my advisor says that Turing Awards are not transitive, so I don't have the Turing Award. So he has the one who has the Turing Award. So today what I'm going to talk about is a field of machine learning which is called adversarial machine learning. And just to give you an idea of the scale, how it has exploded in the last few years. One of the co-chairs of ICML, which is a major conference in machine learning, Kamalika Chaudhary, she and I worked a lot together. She said that there were 560 submissions they got just on adversarial machine learning. So the interest in this has completely exploded. So I'm going to talk a little bit about my work in that. So the plan right now is, I don't know how many of you know some of the adversarial machine learning work. So the first 25 minutes is going to be sort of cliff notes of adversarial machine learning. And the rest of the talk is some of the work that I'm doing with Sanjit Sesha and Tommaso Drusi from UC Berkeley. And there's a lot of slides here that I got from one of my collaborators, Nicholas Paperno, who's right now at Google, but going to be joining University of Toronto. Ian Goodfellow, who was at Google. He just moved to Apple to start a machine learning group. And Jerry Zhu, who's a machine learning faculty in our department. Okay? Just sort of that I like to have questions as the talk goes on, so I think please interrupt me. I kind of prefer the talk that way. And another thing, it's a very fast-moving area. So if I don't mention your field or your paper, it's like by the time I give this talk, there'll be probably 50 archive papers that talk about some of this stuff. So just it's going to be stale by the time this lecture is over. Okay, so just to give you a little concept, I don't need to sort of say this. Machine learning is being used everywhere, but circa 2013. If you remember, there were a lot of articles that machine learning is beating humans at a lot of tasks. I don't know whether you guys remember that. There were a lot of articles that, hey, they're reading medical readings better, they're recognizing faces better. Actually, they were getting better at doing captures than humans. And that's why you see these captures, which barely I can actually pass. Sometimes, they say, okay, I don't know, is that a street sign or not a street sign? I don't know. And this is more for my parents. My parents wanted me to become a real doctor. So that's one of their big things. Even now, they say, he went into the wrong field. He should, because a lot of my cousins are actually doctors. And there were a lot of, and I sent them this slide. They were not very impressed. But in 2017, there were a lot of these articles that actually, for a lot of medical tasks, machine learning was beating a lot of the trained doctors. Okay, and machine learning was used in a lot of adversarial settings. How many of you know this Microsoft chatbot example where with a very little data poisoning, it started tweeting some crazy things? And a lot of the YouTube filtering, they filter content, can also be sort of bypassed by very little editing. And obviously, machine learning is used in a lot of safety critical systems, like robots and so on, so autonomous driving. So at the same time, the security guys, don't like, they mostly like to break things, right? So that's kind of our job. So they saw that a lot of the machine learning, if you look at all the generalization bounds and so on, they say, okay, there is some distribution from which my data set is being sampled. Okay, so what does the security person, as soon as they see that you're relying on some assumptions, they start breaking them. And this sort of started this field of adversarial machine learning. And I will tell you, so basically, at a very high level, you can think about adversarial machine learning as basically saying, no, in most settings, your data is not coming from any distribution, and the adversary can control it. So this is a monster from paper in CDPR from the University of Michigan. This is not my paper, where what they did is they took actual stop sign and defaced it. They tried to deface it so that it looks like some college kid after a Friday night of binge drinking might do the same thing. And essentially, all the object detectors started thinking that this is a speed limit sign. Okay. So you can imagine now if there's a car depending on this, and then they will not stop. So this is a very interesting paper. This was the first paper that I know that they actually physically carried out an adversarial machine learning attack. Good. But I wanted to say that adversarial learning is not not new, although it has become hot because of deep learning. There was a lot of work by Lloyd and Chris Meek on problem of spam. So, if you have seen in spam detection, you occasionally will get some weird message, and those things are just trying to test the detectors and try to bypass it. Okay, so there's a lot of work going on, but with deep learning, things have sort of taken a sort of a new twist, if you will. Okay, so a little bit about adversarial machine learning. So this is a cartoon in some sense of a machine learning pipeline. You have your data set X. You run your favorite learning algorithm. You set it to TensorFlow. You learn some parameters. So that's like the check mark. And then once you have a machine learned model, you say, okay, is this a cat? Is this a dog? Is this whatever, right? So that is basically the prediction Y. Every step of the pipeline, the security people have attacked. So I already talked about training set poisoning. So with very few examples, I can make you which I control by poisoning the data set, I can make you learn very different models than what you would learn. Okay, I saw you that chatbot example that I showed you. We will come to adversarial examples later. One thing I can do is, if you have looked at Google, Amazon, and so on, they are selling machine learning as a service. So that you will have a model in the cloud, and you will have per query pricing models, and they'll say, okay, hey, am I supposed to get diabetes or not, or so on. So the idea is this is called machine learning as a service. And the security people have shown that with very few queries, I can actually extract that model. And then your business model is all gone, right? I mean, why the heck should I pay for it? And I will talk about adversarial examples a lot. It's basically specific examples like that stop sign to give you bad predictions. Okay, so just so that I set up, this is kind of the machine learning, 2-slide machine learning, because I will use some of this notation. I'm going to work in the supervised learning setting. And I have a sample space, which is, think about it as images and labels. So X is all the class of images, Y are all the labels, and I have a distribution that is over X cross Y. So, hey, this is a cat, this is a dog, so on and so forth. H is my hypothesis space, because I'll be using some of this. So think about H as all the weights of your neural network, okay? And you have a loss function which says how good is the hypothesis in predicting things. So, for example, a 0-1 loss function will say that if something is a cat and you say it's a dog, you will get penalized. And the idea is to minimize the loss function. And sort of in the most basic setting, the learner's problem is to learn a hypothesis that minimizes the loss over the expected value of taking the data from the distribution D. Obviously, you don't know that. And then there is some regularizer term which basically says that, for example, if you want to learn a sparse regularizer, then you will say that a lot of my weight should be 0, for example. Okay? So most of the time you don't know that distribution. So basically what you do is you take the sort of the empirical version of that, and you will, this is just approximating the expected value with this sum. That's it. Okay, so this is going to be very important for the attack. One of the main ways of solving this is using something called stochastic gradient descent. And I don't get into it too much, but essentially at each step in the SGD, you will take a step in the opposite direction of the gradient of the loss function. That's all you need to know. And at the end, you will find your best neural network, and you will start predicting what's going on. Okay? And generally what happens is the last layer of the neural network is what is called the softmax layer. So it gives you probabilities of various labels. Like this cat is with label 0.9, dog with 0.05, and you will take the max prediction. So that's all you need to know about the machine learning for this talk. Okay, good. Training time attacks. So we'll get there. So this is the example from Jerry Zoo. So I don't know if that's true here. Madison gets a lot of snow, and our lake freezes up. So these are sort of the number of ice days by year. And if I fit a linear model through it, do you think the line goes up or down? Because of global warming, yes. Good thing there are no deniers out here. And I did a Google search on, this is the top image on the climate denier when they put it Google, so I just put it in. What you can do is you can see that, yes, the model, the blue one is the new line that does go down. But let's say somebody gets hold of your data, who's a climate denier, can change very little of the data set, and the linear classifier goes up. Okay, so this is a classic poisoning attack. So here is what the formalization of a poisoning attack is. Alice is the good person. She picks a data set of size M, gives it to Bob, who's the bad person. He will pick some fraction of points from that data set and poison them, change them. And the idea of Bob is to maximize the error for Alice. And Alice's goal is get to learning from the clean data as if there was the clean data. Okay? Now this is not new. So, this is something I'm finding as I'm getting into field. In computer science, nothing is new. Everything is rediscovered and sort of repurposed. So this field is not new, but has resurgent because of adversarial machine learning. It's a field in statistics that goes back to 50s and 60s called robust statistics by Peter Huber and Ron Chetty. And there the idea was not, obviously there was no deep learning back then. I don't know whether, were there computers in 50s? I think there were, right? But, there was definitely not deep learning. There the idea was that, people lie on surveys, right? If you say, like there last time, remember the McCarthy era. McCarthy actually is from Wisconsin. And somebody asks you a survey saying, are you a communist? Well, a very large percentage of those people will lie. So the idea is that you want to still get good statistics where you know a certain fraction will be bad. But what has happened is, in the recent years, so the statistics guys didn't know how to do this on very high dimensional data. There has been, and I would really recommend this, there has been sort of a breakthrough by some theoretical Fox Talks type people on learning robust statistics on high dimensional data with provable guarantees. They can essentially match lower bounds. So I will not get too much into it, but there has been a huge amount of work in this space now. Okay, now coming back to model extraction. As I told you, here there is a machine learning as a service, and people want to steal your sort of model. So the idea here is that you have a classifier F sitting in the cloud. I can query the classifier with very few queries and learn a classifier that is very close to F. That's what's called model theft or model extraction. And there is a paper, very interesting paper in Usenix Security 2016 by Florian Kramer from Stanford and some guys from Cornell Tech that showed that with very few number of queries, they can actually extract these models. So once you extract these models, it's over, right? I mean, why the heck should I pay Google or anything? Okay, so now there are some attacks which I don't know how to classify them. That's why they were not there. These are called fake news attacks in the literature. And the idea here is that, for example, I can take a picture of Obama or a video of Obama and generate a fake video of Obama saying he's a Muslim using generative adversarial networks. And actually, it was amazing. There was a student in my graduate class who did this as a graduate sort of his project. And I was not able to tell that it was a fake video. Okay, so you can imagine a lot of these things are being used to embed in the tweets and so on and so forth. So I didn't know. I don't know how to call these. This is not misusing the machine learning, but it is using machine learning for bad things. So if you have a good name, I call this fake news attacks. But if you have a better name, I'm open to that. Okay, so this is going to be the more focus for us is test time attacks. So here the idea is that you have a test input, and I want my model to misclassify it. So the definition is that adversarial examples are inputs to the machine learning model that an attacker has intentionally designed. So this is very important to cause the model to make a mistake. This is not what you will see in a normal distribution or generalization error. This is something that I actually am constructing to screw you up, like that fake stop sign. Okay? So the first things that came up, the first paper was from Google, and they took the best machine learning model, and that I will show you how to add that noise. And they were able to take, like Google was trying to advertise saying, oh, you give us a picture, we label it for you that this is a panda, this is a mother with a baby or whatever, right? And they were able to add very little noise for it, and then it was totally screwed up its prediction. So that one was Panda, it became Gibbon. Okay? Now, initially, the way they pitched it, it was not adversarial machine learning. They said, this is weird. If you're going to use this in other settings, this is weird that I can add very little noise, and this is mispredicted. Another one, by the way, there are galleries of this, if you're interested. Like the school bus becomes an ostrich. And my favorite one from last year's ICML, because my wife is into doing a lot of homemade guacamole. So this is like a tabby cat that becomes a guacamole. Now, the good thing about this attack is that it was all done black box. So I don't even need the model. So from the optimization, guys, this uses a lot of things from gradient-free optimization where you are approximating the gradients using black box queries. This is a very good example of that. So this was totally done just using the Google API by the MIT students and not knowing the model, just black box queries. So this was kind of very impressive. This was in ICML last week. Yes?
So the black box query, I'm curious, so you're feeding an input and the output is
Just a label.
But it's the probability of the label, so you can find.
So you get top, at least in the Google API. By the way, Google API keeps changing. So I don't know. I'm telling you what these guys. So it basically tells you the top K, sort of the top K classification. What are my top K labels? I don't think it's numerical. So I think I'll give you 2 minutes. Sort of. It's actually not. It looks very impressive. It's not. There's this field in optimization called gradient-free optimization, and it's basically what it is that you are estimating the gradient by some expectation over just using black box queries. But once I know I can estimate a gradient using black box queries, then I can do all the attacks that I need. I'm in the white box setting. That's kind of the key idea of this thing. Okay. Adversarial examples have gone beyond deep learning, beyond vision, malware, medical images, so on and so forth. Good. I'm not going to go into this too much. The threat model here is, as I told you, white box. It means that I have a complete access to the classifier. I can do gradients, whatever. Black box means, which I just showed you, you just give it an image, it tells you the label. There is also gray box where you know a little bit, maybe the architecture of the classifier, but not actually the weights and so on. So all these three have been actually explored in the literature. So the first attack, okay, this is like so simple that it is amazing that it works. So remember, our SGD step was essentially taking a step in the direction of the negative gradient of the loss function. So what is the opposite of that? I'm going to take a step in the positive direction of the gradient of the loss function, right? Because the attacker is trying to do the opposite. It's like when my son was 2 years old. We used to tell him stuff that he should not do, and he will sort of because he negated whatever we told him. Right? It's just exactly the same thing. The attacker, basically what you do is, it's so simple. I take the gradient of the loss function with respect to the image that I'm trying to sort of, like the cat image. I take the sign of it, and then just multiply by a hyperparameter epsilon. So if the gradient is positive, then this will go in that direction. So the way to think about this is that it is basically doing opposite of what SGD was doing. That's it. And just you can imagine, this is like the state of the the state-of-the-art neural network models. All those things I showed you, the gibbon becoming ostrich becoming gibbon or something, just generated using that noise. Okay. So this, for people who are interested in this field, this is basically considered the most powerful white box attack. And essentially, from the optimization people in this community, it's basically projected gradient descent. So what you do is you use your FGSM model to go outside, but then you might go outside the epsilon bar and you project it down. That's all it is. And this is, if you're going to do work in this area, this is the best attack out there. Okay, so I'm not going to go too much into it. Those attacks were all untargeted because a cat might become a guacamole, a bus might become a school bus might become an ostrich, but you don't control the label of the final attack image. It might become an ostrich, but it might become a lemonade, whatever. It doesn't matter. So we were the first ones, if I remember correctly, which we had a targeted attack, which you give us, hey, I want the school bus to become Indrajit, and we will generate that sort of noise. And we found that it was actually just quite easy. And I'm not going to go into this, but essentially, from optimization perspective, what we are doing is we are doing a coordinate descent on the pixel space, and we change pixels that will give us the closest to the target. It's basically coordinate descent over the pixel space. By the way, a very good, I was extremely, so when Nicholas was giving this talk, just a little anecdote. I like to sort of sprinkle my talk with anecdotes. The keynote speaker was Adi Shamir at that conference. So this is the S from the RSA. And I was like very sure that he was not liking the talk because he was looking and he was shaking his head, this and that. And I was like, okay, he's going to come back to us and he's going to just lambast. And he just came back to Nicholas after the talk and he said, that was fascinating. So I was, so that's like, so Nicholas did a very good job on that. Okay, now there have been many more. I would not use this attack right now. This is dated. Carlini Wagner have an attack which uses a very powerful optimization engine called Adam, which TensorFlow uses, which is the best targeted attack in the literature. Now, all these attacks were white box. I needed the classifier. But I think you can imagine that, if you're an autonomous driving, well, Tesla is not going to give you their classifier. I might buy a Tesla and interact with the Tesla, but I cannot call Elon Musk. First, I don't think he will take my call. But, let's say I call Elon Musk, say, hey, can you send us your classifier? They'll say, screw you, right? And essentially, what we wanted to say is that are these attacks possible to do black box, where I can just send it an image, I get a label back? And the answer is yes. And this was really surprising to us. And the idea is dead simple. The details are sort of wrong. So imagine this way. So this is the first thing. So what I do is I don't know what classifier you're using in your Tesla car. I don't care. I will take the best image classified out there, let's say Inception V3, and whenever I need a label of something, I'll ask you. So I'll train my substitute model using you as an oracle. Once I have my white box model, what do? You can just use all those things. And what happened is these space of adversarial examples has been big enough that the adversarial example on the substitute model transferred to as an adversarial example on the learned model. This was like fascinating to me, and this was mostly Nicholas's observation, and now this is becoming, people are trying to understand this transferability phenomena. There are papers that have come out, and why do these adversarial examples transfer across substitutes? That's the basic idea. I'm not going to say too much. And that's about sort of it. Again, the best so this was the first black box. As I told you, this talk will be stale by the time it's given. The best black box in what I know is that cat becoming that guacamole, that picture I showed you. It's from those guys from MIT. It's called black box adversarial attacks with limited queries, and it essentially uses that gradient pre-optimization trick that I talked about. Okay? Good. Okay, defense. This is NBA playoff time, which Our Milwaukee Bucks are doing very well, so that's why I put this in. So this has been very elusive. It has been super elusive, the defense. And here is my exhibit. So I'll run this as a courtroom. There is a conference called ICLR, machine learning. There were 8 papers that were published on defense for these kind of attacks. By the next ICML, 7 out of these 8 defenses were broken by Athalai, Carlini, and Badger. Okay. Just imagine, it's, I think, 4 months between the conferences, ICLR to ICML. And essentially, the way to think about this is, and I'm not going to, I obviously can't go into the paper too much. The way to think about this is that if you make some assumptions in the defense, well, that's the security person first sort of just attacks it. And they got the best paper award. So essentially, the idea is that we don't know that much about what defense works, what doesn't work. It's a very open field. There is one, I'm not going to get into it, but the technique that was not broken was based on robust optimization by the MIT group, Alex Madri et al. And there's a separate group from Stanford by John Ducci that is sort of also pushing that. And the idea is very simple of robust optimization. Remember, in our old, the ML 101 that we had 2 slides, you're minimizing the expected value of the loss. Now I'm going to minimize the expected value. I'm going to draw a ball around my data set and maximize the expected value of the max loss in that ball. Okay. Now, why do you think this helps? Anybody? So there's an intuition, there's proofs, and so on. My advisor always used to say that if you cannot explain your intuition, proofs don't matter. Yes? Yeah, but why does it actually make it robust, the model map?
Well, if the attacker is trying to generate the data point within epsilon, you're taking the max of that.
Exactly. So the idea is that the attacker, basically you're trying to minimize what the attacker can do to you, and this is, attacker is essentially trying to maximize the loss function. Now what happens is that, again, as I told you, nothing in computer science is new. So robust optimization is actually not new. I learned robust optimization from this book by Bental, Karuya, Dombrowski. But the problem is, these guys are, they program, my student says these guys are programmed in LaTeX. They don't know how to program, right? I mean, these guys are mathematicians. So the idea is that for a lot of models, like SVNs and some of the simpler models, you can actually solve that inner max, okay? So once you solve that inner max, I am sort of back in my old expected minimization, I'm good. But with the deep learning, we know nothing. We know nothing about deep learning. We don't know how to maximize that thing. So we are stuck. Like, how do you maximize this thing? Anybody? What do you do? What would you do? Suppose this is a systems problem, not a math problem. So with models like, max margin SVNs or logistic regression, I can actually solve that inner max. It's not a big issue. But with deep learning, we barely understand what the heck it does, let alone solving that inner max. So this was, I think, Madri's big insight. He said, well, the attacker is trying to solve the inner max. So what I'm going to do is replace the inner max with the best attack that I know in the literature. This in the field is called adversarial training, and it's dead simple. All you do is you take your data point xi, before you pass it through your SGD, you run it through the PGD attack to get the worst case example. And you run the SGD on that PGD attack. That's it. So it's basic, and the thing is that if you come up with an attacker that is better, like Indrajit comes with an attacker that is better, you come with an attacker that is better, I can plug that in. I can, instead of PGD, I can use Carlini-Wagner. So this in the literature is called adversarial training, and this has not been broken. Okay? This has not been broken. By the way, every time I write a paper, I always send it to Nicholas Carlini to get comments, to see if he can spot something. He's the breaker of our this community. People are afraid of him. Okay, so people have been trying to now understand what the heck is going on. Why do these adversarial examples exist? And we don't know. The jury is out. There is the first result is not that hard, but there is a result by Fauzi. Actually, they're all brothers. That was kind of weird to me that as brothers you write papers together. I barely talk to my brother. He gets angry at me. And the idea is that, so there they had a lower bound. They basically said that you cannot have robustness and classification accuracy together. If you want robustness to adversarial examples, you have to give up accuracy. Which seems like, think about it as a no free lunch type theorem. We had a paper in ICML, Madhuri had a paper in ICLR, which gives that for some models, you need more data to be robust. Okay? And roughly, if you need n points in the non-adversarial setting to learn, you will need n times square root d, where d is the dimension, to get a min-max model. So this is also not new. There is a very old paper in optimization, actually, which basically says that if you run SGD for enough steps, you kind of converge to the min-max objective. Okay? So this is not new. Again, but these are not for deep learning. This is for toy models, or our result was for nearest neighbors. There is a very interesting angle coming out, which I am very interested in it. Some theory and crypto folks have moved in, and they have basically shown classifiers where a robust classifier exists, but you cannot find it polynomial time. And this is not new. So, for example, the result is so simple, but with theory, what I find is that the results are simple, but the proofs are hard. So the result is the following. If I have a pseudo-random function, fk, think about like a pseudo-random function is basically like a block cipher. Think about AES. In one data distribution, I have my block cipher. The other one, I say 1 minus the block cipher. If you can distinguish between these two, that means you can distinguish between the PRF, which you cannot do. So these guys are coming from a different angle. They are trying to build worst case examples where it is going to be very hard to find robust classifiers. But the jury is still out, and this direction, I mean, if you're theoretically inclined, this is a very interesting direction. To sort of connecting it to sort of old complexity theory results of one-way functions and sort of PRFs and so on. I find it very interesting. And I'll start sort of like the following methods. What I find very interesting here is before pre-deep learning, if you look at the old machine learning work like Kern's, Valiant, and so on, they had already, there was a lot of connection there with cryptography and complexity theory and all that. So in some sense, that old work is coming to bite us back, which is good. Okay, I'm not going to get too much into it, but there's a lot of work now on, if you have a neural network and you give me a point of a stop sign and say, hey, you want to verify that there is nothing in epsilon ball that can be misconstrued as not a stop sign. There's decision procedures coming out. So the verification folks have already also got into it. And I'm not going to get into it too much. Okay, so this is kind of starts here. So what Sanjit and I started looking at this literature, and we started wondering of the following thing. So this is nice, a cat became a guacamole, and a school bus became an ostrich, whatever, right? But what the real sort of cyber physical systems control theorists are interested in is, does this really screw up my system? Because an autonomous car is not just a camera. It has a lot of other sensors. The the control loop there is actually very, very complicated. And so in some sense, when I do this stop sign, that freak stop sign that I showed you, does this actually screw up my Tesla? That's what we were interested in. And what we found it does not. Because a real car, autonomous car, has LiDAR, pulse detector. The logic is very, very complicated. And so the genesis of this is that I gave a similar talk at the annual conference for the Control Kitty people. And they said, well, this is all playing games. How do you know this actually screws up your control loop? So this is what was genesis of this stuff. And we said, okay, can we do that? Can we generate adversarial examples like a stop sign or something else that actually screws up the whole loop of your program rather than just screw up the camera? Okay? So Sanjit has a lot of connections to the automotive industry, so I'm going to start out with this emergency braking system. They have a model that they got from Toyota, and the idea is that your environment is some traffic sign, and then you use some object detector to say, is there a car at what distance? That goes into a controller which sends a signal, which goes back to the environment. So this is your sort of a closed control loop. And the idea is, can I generate things here by maybe moving the car here, there, where this whole control loop is screwed up, not just this guy. Is the problem clear? And you see that this is a much harder problem than sort of just doing the first thing. So and again, a lot of this stuff came because of talking to these control theorists. So remember, the only kind of transformation we allowed for adversarial machine learning was adding a vector, right? Changing an image, add a delta to it. So in this sort of, in this community, this automotive driving control, automatic control stuff, what they were interested in is more other kind of transformations as well. Can I move the car, make it more cloudy? Can I put a tree nearby? And that screws up your stuff. So the transformations is not just adding vectors, it's actually really transformations on the image space. Does that make it interesting? So the thing is, can we now do adversarial machine learning where we don't allow just this transformation, we allow these rich transformations? Is there anybody from vision in this? So this is to me, this is very similar to domain adaptation, which a lot of the machine learning vision people look at. You don't want to train your object detector in Seattle and it stops working in the Bay Area, right? So the domain adaptation means that your machine learning models, and to me that is very similar. You basically, these semantic transformations are essentially codifying the domain. And if you guys, there's a lot of work now going on in CVPR and also ICML where they found that the adversarial training that I showed you before is actually improving domain adaptation. So there's a lot of interesting space. So this is very much like, to me, this is like adversarial domain adaptation. You want to sort of create a domain where it screws up your detector. Great. So for example, what we found is that this is a semantic perturbation. So I take a car and I move it to the next lane. Now, if my detector says there is a car here and says there is no car here, well, that's not good, right? So these are the kind of transformations I want to look at. And this is much harder because how the heck do I solve the optimization problem? Okay, theme 2. So this is what I was telling you about. What we found is that if you look at both these images, it fooled my object detector in the loop. but only one of them actually made the car brake because some other control thing in the control logic picked it up. So this basically shows that every adversarial example is not an adversarial example for the full control loop. Okay? And well, you know, what you can now do is, if you find these adversarial examples, you can use them to retrain your network like we did before. And that's what Susmit and his postdoc did in, they have an IJCAI paper from last year that basically showed that if you take these examples and feed it back to the object detector, your control loop totally becomes robust. Okay? In some sense, you're feeding the counterexamples back into the machine learning engine to sort of feed that. Okay, I'm not going to go into the experimental results, but basically say everything gets better. Nobody shows bad results, so I've stopped looking at the experimental like, yeah, everything goes up. Yes, good. Okay, so theme 3. There is a lot of work in, what time is it? I have to cover quite a bit. So I need to know when to, okay, so I will stop. I have, so the thing is, so the idea here is that this machine learning models that are used right now in the controllers are totally black box. They basically say, oh, there is a car, there isn't a car. And the idea here was, if you somehow give me more information and make the controller white box, can you do better? And there's some work on that. But I want to kind of get into sort of theme 3, where is what I'm really looking at is, was the theme of the talk, can we generate adversarial examples that matter? Means that they actually do the control loop. And here, going back to my formal methods route, here is the problem. So you are given a formal specification P, and you have given some model M. And the idea is I want to find the example that makes this model falsify this property. This is called compositional falsification in the formal methods community. So the idea here is that we know how to do this without machine learning. Okay, the CPS community, the model checking community has looked at it a lot. So the problem here is, how the heck do you treat the machine learning component? So can somebody guess how big is the Google, the biggest ML model at the image detector at Google? How many parameters does it have? Can anybody guess? It has right now 30 to 40 million parameters. So imagine the state space. And they are now talking about models and object detectors with a billion parameters. Okay? So just imagine modeling that in your loop. So we don't want to be in the business of modeling machine learning components. So what can we do? Well, once you train a machine learning model, it is a program. So we know how to handle programs in programming languages, so we just treat it as a program. But there, I already told you what the problem is. The state space is too large. Okay? The other is the following, and these are the straw man that I'm trying to build up, is that I use my adversarial machine learning model, like PGD or so on, get adversarial machine learning examples, and then feed it through my checker to see, is this really adversarial? The problem is the percentage of examples that are actually adversarial for the whole loop is very small. So I'll be doing a lot of stupid work, okay, and a lot of extra work. So in some sense, I will just give you, I cannot get into full detail. It's that you don't want to be in the business of modeling machine learning models. You want to use them as a black box. And what we generally do is, this is a very clever idea that these things, I'll just kind of give you a sort of an idea of this. So by the way, these models were generated, this was an adversarial example for the machine learning model, both of them, but only this one caused the crash, the break to crash. And the idea is very simple. well, I mean, simple to describe, but hard to carry out. So what I'm going to do is I'm going to assume that the machine learning model is always wrong first. Whenever there is a car, it says there is no car. Okay? So this is generally in formal methods. This is called pessimistic abstraction. Then the second one, I'm going to always assume the machine learning model is right. When there is a car, it says it's a car. Okay? So that's what this is doing. So when the machine learning model is always correct, this is the space where the braking happens in the car. This is unsafe space. Well, this one means that there is some problem in the logic besides the machine learning, because it caused your machine learning program because the machine learning program was perfect. Here, the machine learning was wrong, so this space was slightly bigger, and the intersection of that space is where we can look. So in some ways, you take the space of optimistic and pessimistic abstractions and you kind of subtract them. And if you overlay this over this, you will get this. And this is where I need to look, because here, I know that even the machine learning model is right. This program screws up, so there's something in the logic. So this really drastically reduces the state space in the machine learning model that we have to look at. And that is what we generated a lot of these images for. Okay? So this, I think, to me, this is where the community should move. Otherwise, it's all games. Like if you're generating images, yes, people laugh, cat goes to guacamole, this and that, but we don't know that they actually screw up your car, sort of the control logic. Yes? No, we actually, so remember, the idea here is that we will not exhaustively search here. As long as we find few counterexamples, then we'll feed it back into retraining. So remember, we are not trying to verify here. This is compositional falsification. So the idea is that I want to find one scenario where the control loop breaks. The full verification problem is much harder. This is a simpler problem. Is that answer your question? That's called compositional falsification. It's like generating counterexamples. And I'm not going to get too much into that, but you can see that if you just did sort of full search, you will be dead. Now, I'll tell you where I think there's a lot of work to be doing. So what a lot of these car companies do is they literally take these models that are out there on the web. And I'm not kidding you. They will take YOLO squeeze that you and I can sort of also download, and they literally just use them. Okay? To me, this is totally unacceptable, right? I mean, why will I know these things are very brittle. What the heck? I mean, you're not a student in a machine learning class. You're Tesla, spend some money. But they don't want to. I think the idea is that these models have been sort of trained over a long time. So they literally take some of these models. To me, that is what is creating the problem. So the idea is, can you actually train these machine learning models with maybe some combination of loss functions so that you're steering the misclassification to what matters towards that yellow zone, and you're telling the loss function that, hey, the other stuff doesn't matter. Because if you misclassify in that work, I don't care. So this is a big field in machine learning emerging, is generally our loss functions, what I showed you before, are all geared towards just reducing misclassification. But that's too narrow, because you can reduce, I can have a classifier that is really very good in classification, but then the robustness will be very bad, or so on. So there is this big field in ML, I think, and which is good, is that you want to optimize the loss function for other things, not just classification. So in that vein, my most interesting paper is, there is a paper group from, how many of you know explainability? So the thing is, what they do is, so explainability, basically, the field emerged because it's saying that I don't want just predictions that this is a cat. Tell me what features were most important in predicting that this was a cat. And the idea is that what happens is if you look at existing techniques, you will get that almost all features will get some weight. So Tommy Jukula and so on from MIT are saying that can we train networks that actually give you prediction along with the explanation. These are called self-explaining neural networks. And they're essentially is that they're modifying the loss function to reduce classification accuracy, but also give you small explanations. Okay? So there is a huge work in machine learning now on saying that we need to train the networks, not just for reducing misclassification, other things as well. And that's what we want to do here. This is totally open. I don't know how to do this. Okay? I personally feel this would be a sort of immediate paper if somebody can do it. So I have 2 minutes. I wanted to say that it's a very, very exciting area, adversarial machine learning. It's totally wide open. Although, as I told you, there's a lot of papers being written, 50% of them not worth reading. But, I don't know which one. A priori, you don't know that. There's a lot of workshops coming up. So, for example, there is an ICML workshop that a lot of us are organizing on this topic. So, if you're interested, sort of come there. 2 websites to follow if you are interested in this field. robustml.org is Alex Madri's blog, basically. And he tries to cover a lot of the stuff. Obviously, it's very MIT slanted, but you cannot fault them for that. MIT people think that that's where their world ends. So that's there's a lot of little bit of arrogance there, but still very good information. And then, if you're interested in attacks, Clever Hans is the toolkit from Google that implements all these attacks like TGD, FPSM. And you don't want, by the way, one thing I wanted to say is that you don't want to implement these attacks yourself. It's better to use it from there because these things have been optimized quite heavily. So you don't want to write the PGD attack yourself. And if you have a new attack, you can actually give it back to Clever Hans. And on that, I will end just to sort of, so that this is exciting area. Hopefully, people here will get involved and interested.
Well, the time's getting late, but fantastic talk. We want to end this session by presenting to Professor Dunn a plaque that you read from it, presented to Shomet Shah in appreciation for your Information Science and Technology Center ISTEC Distinguished Lecture, April 22nd.
Thank you so much.